Hello friends, we will now discuss one of the important topic of semiconductors. Rather than saying important, one of the interesting topic of semiconductors, that is diffusion. Diffusion is basically the flow of charge carriers from higher concentration to the lower concentration. Let us assume one n-type semiconductor bar which is illuminated from one side. When you illuminate this semiconductor bar from this side, what will happen? At this point there will be generation of electron hole pairs. So the concentration of charge carriers at this point will be definitely more than the concentration of charge carriers on this side. So the charge carriers will start flowing from higher concentration to lower concentration. Remember, this is a natural process. Charge flow from higher potential to lower potential. Liquid or fluid flow from higher pressure to lower pressure. Heat flows from higher temperature to lower temperature. So this is a natural process. So the charge carriers will start flowing from this end. Say this is x equal to 0. This is your x-axis. So the concentration of charge carriers, I'll be taking the concentration of minority carriers, that is holes in n-type semiconductor bar, because I discussed in case of generation and recombination as well. When you illuminate the semiconductor bar, the percentage change in minority carriers is much higher than the percentage change in the concentration of majority carriers. So therefore, we consider the concentration of minority carriers. So say at steady state or at far end, the concentration is nothing but P naught. At this end, that is the steady state level of the concentration. Say at this point the concentration is nothing but P0, that is P0, this is P0, and above steady state level, say it is P dash 0, like this. This is P dash 0. So because of natural flow, the charge carriers will flow towards this end of the semiconductor bar, and it will be like this. And finally at large distance, the concentration will become equal to the steady state level. This is the natural variation, exponential variation. We will see that how it comes out to be. So in case of n-type semiconductor bar, this is how the concentration of minority carriers will change. Now, when there is flow of charge, say I am considering holes in this case, when there is flow of charge, so there has to be a current, and that current, because of flow of charge carriers under the influence of concentration change, that is flow of charge carriers because of the concentration gradient. I am not applying any electric field here. The charge carriers are flowing because of concentration gradient, but whenever there is flow of charge carriers, there has to be a current. So the charge carriers are, the holes basically in this case are moving in this direction, even though electrons will also move in this direction. Why? Because concentration gradient is in this direction only, so electrons will also flow in this direction. But considering minority carriers, so I'll be considering holes only. So holes are moving from this end to this end, and that will constitute a current known as diffusion current. And the diffusion current density due to holes in n-type semiconductor bar shown in the figure is given by dp by dx. So what is this? Q is the charge of hole. dp is called diffusion constant. This dp is known as diffusion constant, that is diffusion constant, and dp by dx is nothing but concentration gradient inside the semiconductor bar. Now try to recall the continuity equation. What was the continuity equation? The continuity equation gives what? The rate of change of concentration of charge carriers per unit time, and that rate of change of concentration of charge carriers per unit time, dp by dt, is equal to P naught, that is steady state level of the concentration, minus P by tau P. I am considering holes, so that is why I am taking this. Tau P is average lifetime of holes minus, that is equal to 1 by q dp djp by dx. This is known as continuity equation. Now this can be written like this: p naught minus p by tau p minus 1 by q 1 by dx, and now this is nothing but the current density due to holes, so that is diffusion current density minus dp by dx. So now you can write it further like this: p naught minus p by tau p minus, this q will come out, this will become plus, that is nothing but dp square by dx square. That is what you have. This is dp by dt. That is rate of change of concentration of holes per unit time. But at steady state, net change in concentration, when you have enough time is elapsed, the net change in concentration of the charge carriers is nothing but 0. So I'll rewrite this equation like: at steady state, when steady state is reached, so the rate of change of concentration of holes will be 0. Meaning is I am illuminating the material continuously, so net generation will be equal to net recombination, and rate of change of the concentration of holes will be 0 at steady state. So this gives dp square by dx square is equal to p minus by tau p. That is what you have. Now this gives dp, that is d2p by dx square is equal to p minus p naught by tau p dp. P is concentration at any moment of time, p naught is the steady state concentration. Remember, this concentration level from here to here is nothing but p dash, and that is nothing but p minus p naught. This is known as excess concentration over the steady state level. So p dash is the excess concentration, so I can rewrite it like this: d2p by dx square is equal to p minus p naught is nothing but p dash by lp, where what is lp? lp is nothing but lp square, rather lp is nothing but dp tau p under root, and this is known as diffusion length. That is known as diffusion length of holes. What is this mathematically? How do we define diffusion length of holes? Diffusion length of holes is nothing but average distance traveled by holes before recombination occurs. In the semiconductor bar, suppose electron holes are hole pairs are generated here, then average distance traveled from this end to this point before the recombination occurs, that is known as average, that is known as diffusion length of holes. That is diffusion length of holes, right? So here what is p dash? P dash is nothing but p minus p0. If you differentiate it, dp dash by dx will be equal to, p naught is a constant value, so dp by dx. So it means dp by dx is same as dp dash by dx. So you can rewrite this equation like this: dp dash by dx is equal to p dash, this is square, so you can differentiate it again like this: d2 p dash dx square is equal to d2 p by dx square. So this gives p dash by lp. Now you can find the solution of this, that is nothing but second order differential equation. The solution of this equation, solution of above equation can be written like this: p dash x is equal to, or you can say simply p dash, because I am not writing mentioning at px, this is p dash. So p dash is equal to nothing but some constant k1 e raised to power minus x by lp plus k2 e raised to power plus x by lp. This is the general solution of any second order differential equation like this. So here if you see the two terms, the first term is nothing but it is decreasing with increase in x. Why you are having negative sign here? So concentration is decreasing. Second component gives increase in concentration with increase in x, but that is not a fact. Concentration is more here, concentration is reducing in this side. It means there is no increase in concentration with increase in x. So that means, so this gives what? K2 equal to 0. I am repeating the concept, please try to understand. In this direction concentration is decreasing. If concentration is decreasing in this direction, that means this factor K2 must be 0, otherwise it is increasing component. So K2 is 0. So this gives P dash is equal to K1 e raised to power minus x by LP. Now when, or you can say at x equal to 0, when x is 0, what is P dash? What is this P dash? P dash is nothing but P dash 0. So P dash is nothing but P dash 0. So this gives what? That is equal to K1. So P dash is nothing but P dash 0 and that is equal to K1. So P dash is equal to P dash 0 e raised to power minus x. That is nothing but what is this P dash? P dash is known as excess, that is excess carrier concentration. Remember this. The value above steady state value is known as excess carrier concentration. So excess carrier concentration as a function of distance is nothing but excess carrier concentration at x equal to 0 into e raised to power minus x by LP. LP is nothing but diffusion length of holes. So now you can write, this is important expression you should remember, and there can be conventional question in engineering services on this. You may have to derive the expression of the change in concentration because of the minority carrier injection. This is known as minority carrier injection, when you illuminate and there is generation of the minority carriers. So here now what is P dash? We have already seen that is nothing but P minus P naught. And what is P dash 0? That is nothing but P0 minus P naught. P0 means total concentration at x equal to 0 and minus P naught, that is P dash 0. This minus this. So this gives P minus P naught is equal to P0 minus P naught by LP. Or further you can write P is equal to P naught minus P0 into e raised to power minus x by LP. This can be another expression for IES mains, IES conventional paper, or there can be question in civil services as well. As far as objective type questions are concerned, there can be direct formula on this, but till date you don't have any question directly on this. But concept is important. Concept is what? Whenever there is concentration gradient inside the semiconductor, there is flow of the charge carriers from higher concentration to lower concentration, and whenever there is flow of charge carriers, there is a current, and that current is known as diffusion current, and that diffusion current is important. Here the diffusion current, holes are moving from higher concentration to lower concentration, so the concentration gradient is negative in this direction. So the current, diffusion current in this direction is nothing but having negative for holes. So I'll repeat, diffusion current due to holes, and that is given by Jp is equal to minus Q dp, that is dp by dx. This is your diffusion current. And now the diffusion current due to electrons, so the diffusion current due to electrons is given by, that is equal to, now suppose electrons are moving in this direction. If electrons are moving in this direction, so current diffusion current will be in the opposite direction due to electrons. Diffusion current will be in this direction. In this direction, concentration is what? Current concentration is increasing. Concentration, there is positive concentration gradient. So for diffusion current due to electrons, it is positive, not negative. dN by dx, where what is dN? dN is called diffusion constant of electrons. So these are two very important expressions. You will have a number of questions in exam. Diffusion current due to electrons and holes. Now here there is a relationship between these two. You can see dP and dN can be related if their concentration gradient is same. If concentration gradient is same, you can take these equal and you can find the relationship. We will see that relationship later on. That is the relationship between diffusion current of holes and electrons. So this is all about the concept of diffusion. We will see the questions on diffusion current. Once we discuss all the components of current will be the next topic. But before that, there is one important topic, that is nothing but Einstein relation. This is important from examination point of view. You have a number of numericals. In past there were questions on this, on the Einstein relationship. According to this relationship, the ratio of dN upon mu n is equal to dP upon mu p, and that is equal to Vt by 1, that is equal to kT by Q, where K is Boltzmann constant, T is nothing but temperature in Kelvin, and Q is nothing but charge of the hole, and that is equal to 11600. So this is very important relationship. You should remember K is nothing but 1.38 into 10 to the power minus 23, that is joules per second, and that is Boltzmann constant. Boltzmann's constant. So you should remember this constant. You should remember the value as well. Now at this expression, this value is known as thermal voltage. Here Vt is equal to kT by Q, and that is T11600, and this is known as thermal voltage. Why? Because it has the dimensions, the units of same as voltage. This is known as thermal voltage. Remember this. At room temperature, which is considered to be T is equal to 300 degree Kelvin, the thermal voltage is equal to 300 by 11600, and this is approximately equal to 26 millivolt. So you should remember this. This is important expression, you should remember. This is important expression, you should remember. And relationship you should remember. So these are some of the important expressions which may be used, which will be used in different exams. And it is important from objective type point of view. There is a little rare chance on the conventional question because it is just a formula. So, but as far as GATE is concerned, as far as engineering services prelims is concerned, there can be question on this. You should remember this expression, that is known as Einstein relationship. After this we will discuss, that is nothing but difference in semiconductors. So that will be our next topic. So thank you for watching the video.